Hello and welcome. This is Andreas Antonopoulos from Let's Talk Bitcoin here in Las Vegas for the Inside Bitcoins conference. It's a great pleasure today to have Adam Back, applied cryptographer and somewhat of a celebrity in the Bitcoin space because of his long history of contribution to cryptography in general, but essentially some of the building blocks of Bitcoin. Adam, welcome to the show.
Hi, good to be with you.
So Adam, can you tell us a bit about your history in the space of applied cryptography?
I was interested initially in PGP. When that first came out, I found it very interesting that there were political and balance of power implications between individuals and the state, so that people could change, they could communicate with other people without any possibility for interception, and the ability to communicate privately is essentially a right in many countries. So you can think of it from the point of view that you have some legal rights. You have a right to freedom of association, freedom of speech, but to strongly exercise them, you need to cryptographically enforce them. Privacy technology, end-to-end encryption, things like PGP, enable people to exercise their rights, and the ability to strongly exercise their rights enables people to build a democratic society. I think it's necessary for that.
So tools like encryption also open the possibility for much more creative expression, which nowadays is becoming very difficult. This constant feeling of being surveilled, ubiquitous surveillance is antithetical to democracy. It's antithetical to free expression.
That's very much true. So I mentioned freedom of expression, but I mean freedom of association. So to get freedom of expression, you maybe need encryption so that you can communicate privately between yourself and your colleagues or friends. But freedom of association actually requires another cryptographic property, which would be anonymous communication. So if you have a legal right to have freedom of association, and society recognizes this in law, in fact, in most Western countries, then you need anonymity technology. So you need to be able to send emails anonymously.
You were involved in many of the early developments in applied cryptography, and you don't just talk about the theory and philosophy of cryptography, but you are involved in innovating in both cryptographic applications but also cryptographic algorithms. In fact, you're one of the 6 or 7 people cited in the Satoshi Nakamoto paper on Bitcoin as one of the contributors to the state-of-the-art that came before, specifically with Hashcash.
As I mentioned, I became interested in PGP and then I subscribed to the Cypherpunks list and bought a number of books on applied cryptography. I was actually doing a PhD in distributed systems at the time, but I kind of didn't make much progress on distributed systems for a couple of years. It was a 4-year course and took a big detour into applied cryptography and basically spent all my time learning everything I could about that. Obviously interested in the technical aspects so that, if you know the features available, you can use them as building blocks to achieve new, interesting properties for privacy-enhancing technology systems. So you can look at it from the point of view of requirements. You want certain requirements from the system, so you want to have freedom of association, you need anonymity. Many deployed systems have some non-ideal properties because it's quite technically challenging to achieve some of these properties. So in that context, I also became interested in privacy technology, so for example, anonymous remailers. For a while I ran anonymous remailer, and a problem I observed there firsthand, and obviously other people were experiencing this and concerned about it, was that because it's anonymous, people can create mischief. So I think people are generally happy with the fact that anonymous speech could be unpopular speech. The right to freedom of speech includes speech that you personally find unpleasant or derogatory and what have you. And so people are generally willing to delete or ignore things they're not interested in if they see an anonymous discussion on topics on like a public discussion forum with some anonymous contributors. If the anonymous contributors are being disruptive, they'll generally be ignored and people will be happy with that. But there is also the consideration of sort of denial of service amplification. So for example, Usenet is a broadcast mechanism. So and the anonymous remailer operators wanted to allow people to participate in public discussions anonymously. So there were mail-to-news gateways and direct news posting facilities within the anonymous remailers. And some people, for whatever reason, it's not clear obviously because they were anonymous and they weren't explaining their motivations, would post large amounts of spam essentially to Usenet with no particular meaning, just large volumes of random text and what have you. Basically you could imagine perhaps to discredit remailers, that remailers were a source of large volumes of useless junk that was clogging up Usenet, and every message that goes onto Usenet would basically be brought through a broadcast tree mechanism, arrive at millions of computers on the internet, so the overall volume of network resources used was quite large. I was kind of thinking about that problem, and I happened to be reading about birthday collisions in hashes, just as on a technical basis, and it occurred to me that a full birthday collision, say on SHA-1 at the time, it takes approximately 2 to the 80 operations to create, so it's an immense workload to create that collision, but once you have that collision, you'll be able to demonstrate it to somebody, and they'll be able to verify it in almost zero time. I mean, in about the same amount of time it would take you to process a TCP packet, a few thousand cycles on a CPU. I thought, well, that's interesting. There's an ability to prove work there. Maybe I can modify that algorithm so that I can have a scalable proof of work, a proof of work that I can, say, force it to take 1 minute or 10 minutes instead of a billion years. And so I set about changing that algorithm, and now one aspect of birthday collisions is to compute them requires large amounts of memory, and there's a time memory trade-off, in fact. And I viewed this as a somewhat unattractive property, so I try to avoid that and switch to exploring partial preimages.
Can you explain that a tiny bit, what birthday collision is and what partial preimage is?
So a birthday collision, it refers to the kind of surprising statistical phenomenon that if you go to a party and you wonder what is the probability that there will be 2 people in the room with the same birth date. Assuming birth dates are evenly distributed throughout the year, surprisingly, and there are 365 days in the year, surprisingly you only need 23 people in the room to have the same birthday. Now, for large numbers, you can approximately estimate that if there are 1 million days in a year, you need about 1,000 people in the room, so it's approximately the square root.
Right.
And so when you're talking about cryptographic hardness, you're saying, so SHA-1 has an output of 160, so it has 2 to the 160 work operation to do a full exploration of its key space.
That's like a brute force of trying every possible output of SHA-1 to produce it. Yeah.
So if you're looking for a birthday collision, the way you do that is you compute lots of candidate inputs to SHA-1 and get the outputs, which are essentially random. You store them in a big table, and you keep doing that until you find an output that's the same. So because of the birthday principle that we just described, you would expect to do that in 2 to the 80 operations, and not 2 to the 160. But of course, that implies 2 to the 80 memory or storage, which is a vast amount of storage. And there are trade-offs where you can do more work and store less, and there are also cycle algorithms.
One example of that is in the coin business, we have 2 coins that have drastically different proof-of-work functions, SHA-256 in Bitcoin, and then Scrypt in Litecoin. Scrypt is much more memory-intensive, less CPU-intensive, and SHA-256 is all CPU.
Let's back up a bit to Hashcash. So originally, I just modified the algorithm, so to connect it to a service, so you're trying to obtain service, so you want to create a proof of work essentially from this, but that is bound to a service. So you have a service string, let's say an email address, a remailer address, a Usenet news group, and in Bitcoin's case, the Coinbase. And you vary something inside that, so a counter or something, and then you repeatedly hash it until you get a given output. The original proposal was to hash the service descriptor alone to produce one random output and use the leading bits of that as a fair challenge, and then you'd use a counter in the second one, and you would change the counter until you find an output that matched the first one. So that's a kind of fair challenge concept, and at some point 2 people, Hal Finney and a guy called Thomas Boschlu, independently suggested that you don't need to choose a fair challenge because any arbitrary string like the digits of pi or the all-zero string is also a fair challenge and slightly simpler. And then to verify the proof of work, you only need to invoke 1 hash rather than 2 hashes to be able to compare the strings.
Out of this, Hashcash was born, and the concept, as I understand, and please explain it to us if I've got it wrong, is that by forcing people to do a bit of work and then proving that they did a bit of work before sending mail through the remailer, that puts a minimal burden on someone who's sending a message with content because they have the commitment and incentive to do it. But for someone who's just spamming, it would put an unreasonable burden, and that doesn't scale.
We talked about the context of remailers, and it was used for that for some period of time, and also as a anti-spam mechanism for email. So people who are spamming are often they have a profit motive. And so it matters to them how many mails they can send per second with their given resources. So, they'll use thousands of BCCs in the headers to amplify the amount of mail they can send by having the mail server do some work for them. And they will max out their network resources and so on. So what you can do with Hashcash is if each recipient of a mail requires a stamp that is bound to their email address, that means that somebody who's sending an email can't reuse a Hashcash stamp to send the same mail to two different people. So they're using a unique stamp for each recipient. And so a number of these tricks, like using BCC to have a mail server sent to lots of people at the cost of the traffic between the spammer and the mail server, only going over the network once and sending to 1,000 users, that's avoided, right? Because 999 of them would reject the message if there was one stamp on it. Basically, it's an economic argument that whatever their profit margin is, which is obviously very slim because very few people would actually act on these spams, but they can operate with 1 in a million clicking through and getting $5 from that because their cost is some tiny fraction of a cent. So by requiring a proof of work, there are only so many proofs of work they can do in an hour, and so the number of mails they can send per hour maybe drops by 1,000 or 10,000 or 100,000, and you can vary the proof of work to tune this effect. So basically you want to have as high a proof of work as is not inconvenient to a regular user who is not engaged in spamming. So if you're sending an email to a friend or colleague or family member and you click send, it takes 30 seconds or a minute. If it's computing the stamp while you're composing the email, you're essentially not really going to notice and it's not going to get in the way. Another thing to consider about the Hashcash proof of work is that it's non-interactive. The challenge that you use to compute the proof of work is done on your own computer. You don't need to talk to anybody first. So you don't need to contact your recipient or the web server that you're going to provide the proof of work to ask it for some challenge or something to work on. You choose randomly a fair challenge. You provide a proof of work that you did work on that challenge, and the challenge also involves the recipient's resource name, and then you send it to them. So that makes it basically, in distributed systems terms, 100% scalable. There's no new communication overhead, so it can be used in essentially any protocol and scale to internet scale. It could be used in email without having any communication effect. People used it, apart from remailers and mail, it was also used in larger quantities for name squatting. So the I2P anonymous networking protocol, which is a kind of Tor competitor, has a pseudonym concept, and to obtain a pseudonym, produce a much larger proof of work. So that's basically to discourage name squatting, because people come along, they could ask for names cheaply at no cost, and so they would try to take all English word dictionaries or all common names, and then there would be no interesting names left. And you can see an aspect of that within Bitcoin. So Bitcoin has to contend with the Sybil attack, which is that when it's voting which transaction is correct, so you've got many people in the network and you somehow have to agree amongst this distributed system which payment is correct, which payment came first, and that the payment is valid with respect to its preceding transaction input. The same situation as name squatting, an analogous situation exists for Bitcoin, which is that if somebody has an interest to influence the vote, saying the vote is just a one person, one vote, or one computer, one vote, they can do a Sybil attack. So, if the system is looking at IP addresses to try to enforce one person, one vote, it's very easy for people with a botnet or cycling IP addresses to perform what's known as a Sybil attack, which is that one person can pretend to be a million people and get an undue amount of voting. So Bitcoin uses the proof of work to say, well, you get one vote per CPU cycle, essentially. So it's not fair in the sense of one vote per person, but it's less abusable than the situation of one vote per IP address or something unenforceable. So at least it's strongly enforceable, shall we say.
Hashcash, you first published the paper in 2002, and then in 2008 it was cited in the Satoshi Nakamoto paper, and Satoshi suggested using it in order to do proof of work on a coin, a digital cash system, which is probably now the most widespread application of the concept of proof of work, and certainly one of the most successful we've seen. The original concept of one CPU, one vote. Now we've seen this enormous explosion in hashing power as we very rapidly, because of the economic incentives existed, and there were very good economic incentives, we've moved very rapidly from CPUs to GPUs to FPGAs and now to ASICs. And there is some concern in the community at large, and some discussion, a recurring discussion, probably a very good discussion to have, about the risk of centralization, about the possibility of organizations with economic resources to acquire silicon from fabs to be able to create massive proof of work farms, essentially, and either dominate Bitcoin with a nefarious purpose or simply dominate mining in order to funnel a lot of rewards in their direction. Do you share that concern? Do you see the argument, and what's the risk of centralization?
Yeah, I do share that concern, and actually when I first joined the Bitcoin Dev Forum earlier this year, my reason for joining was to articulate this exact concern. And so my concern was that, and I guess many people arrive at this concern, is that because using SHA-1 as the hash function in Hashcash, the proof of work used in Bitcoin, because it's so simple, it's easy to run on FPGAs, GPUs, ASICs, to a significant and dominating advantage compared to less specialized hardware.
Like a general purpose CPU.
Right, so I mean, we saw initially, the initial version of Bitcoin, people were mining on a CPU. Quickly, people moved to GPUs, and after that to FPGAs, and then ASICs. And each move typically will render the previous generation of approach of mining type of hardware used completely unprofitable. It means that over time, basically you can't mine unless you have an ASIC. And so CPUs, everybody has CPUs and they have multiple uses. GPUs, you can generally get GPUs because people want to play games with them and video games and what have you. But as I understand it, there were also supply problems with GPUs because Bitcoiners were buying up the entire stock of GPUs, but at least that's something that consumers, the man in the street, can have a fair chance of buying, as opposed to, let's say, a large company monopolizing the supply or something like that. So that's potentially an argument for scrypt, so to replace SHA-256 in Hashcash. So just to back up a second, many cryptographic algorithms are based on building blocks. So we have building blocks such as SHA-1, SHA-256, AES, and so on. So, for example, with HMAC, you have HMAC SHA-1, HMAC SHA-256, HMAC MD5, and so on. So with Hashcash, it's very similar to HMAC. There's Hashcash, and the original Hashcash was using SHA-1. Bitcoin uses Hashcash with SHA-256 iterated twice. And scrypt uses Hashcash with the scrypt internal hash function. I think there's a slight confusion about scrypt, because scrypt used for its original purpose is to stretch passwords, to make passwords harder to grind. And in that context, the scrypt has an iterator, typically 10,000 or 100,000 time iterations. And so it has its own hardness, but that hardness is not being used within Litecoin and other scrypt users. Hashcash scrypt is really Hashcash and the internal scrypt function, or scrypt iterated once, essentially. So it makes use of the memory hardness, but it doesn't make use of the scrypt iteration. And the reason that you can't do that is if you used scrypt's hardness by using scrypt's iterations, then when you came to verify the proof of work, you'd have to repeat the work. So it would have an extremely expensive verification time. So there's a Hashcash using SHA-256 versus Hashcash using the scrypt internal hash function debate. The argument is that because the scrypt hash function artificially consumes memory, it does actually have a time memory trade-off, but it's still more expensive in terms of memory, that it should be more resistant to implementation in ASICs. And so people use that as an argument to say that scrypt using Bitcoin clones may be more interesting, or may be more resistant to centralization risks. However, there's an interesting counter-argument, which is that SHA-256 is a very simple algorithm that was originally designed to be simple to implement, simple and efficient to implement in hardware. And there are circuit layouts for SHA-256 available for free download on the internet. So potentially even somebody with relevant industry experience or academic experience in circuit hardware could make a small run of mining hardware themselves with their own savings. Conversely, with scrypt, because there's a barrier to entry, it turns out it's not impossible to make an ASIC implementation. And in fact, there are rumors that, and even announcements, the two companies are doing just that right now. So as that succeeds, there's actually a much larger technical barrier to entry to create Scrypt ASICs. So it actually turns out that the centralization risks are actually worse with Scrypt.
Because only the specialists will be able to design those circuits. There'll be more limited supply.
So, I mean, for example, it needs low latency memory, and the circuit design is much more complicated. And another aspect of this argument is that, well, in an ideal world, you want tens of thousands of people to be mining. Power users in their garage, people mining just for curiosity on a GPU or on a small ASIC, a USB ASIC, and we see some of those, just so that the mining power is distributed, because there are specific risks that arise when policy risks, and I'm possibly less concerned about the profit risks, because basically anything anybody does to mine more efficiently means that the overall resources consumed to complete the Bitcoin distribution until we get to 21 million will consume less electricity and result in somebody getting some profit, which hopefully they will reinvest in the Bitcoin industry or in general. Whereas if everybody is mining less efficiently, more resources get consumed, and so there's less money released to Bitcoin-related industries. So the argument for ASICs is, so will we get decentralization with ASICs? So the question is about supply, and there are some interesting economic dynamics in there. So if somebody has put the minimum investment to make some ASICs, they have some incentives to consider, will they mine them themselves? And people's first reaction is typically that, well, this is a machine that lets you print virtual $100 bills. Why would you sell it? Surely you'd use it to mine as fast as you can and keep the proceeds. So one counter-argument to that is the mining profitability once the system bootstrapped, perhaps after the first 3 or 4 years or so, the mining profitability margin dropped considerably, so there are actually risks to mining. So, for example, many people ordered ASICs from companies on pre-order, and by the time the ASICs arrived, it was kind of debatable whether it was even break-even, that they would be able to, for the electricity cost, recoup their hardware investment. Now, the other dynamic is that people who are selling ASICs, there's a question of the hardware manufacturers that are making ASICs. I initially thought, well, what we need is a Kickstarter so that there is free, ready availability of ASICs if you subscribe to the supposition that people who manufacture ASICs are hoarding them for internal use. So we need maybe a Kickstarter with at cost or non-profit availability of these things to ensure decentralization. But actually the economic arguments that the ASIC manufacturers are operating under are interesting, and their argument is that there's a natural incentive for them to not overproduce and oversupply. Because if they do that, because the difficulty will ramp up, the profitability margin at a given Bitcoin price will drop to close to zero.
For everyone, including their most recently shipped customers who will be annoyed.
Right, and so that will mean that they won't have follow-on customers. People won't buy anymore, or that they'll have to sell them at a slimmer margin. So they'll destroy their own business, and they would remove profitability. So there's a natural shelling point for them to sell at a margin so they make a profit, their customers make a profit, but they don't make too much of a margin, so that somebody else has an incentive to step into the market or optimize their own ASIC, their competing ASICs, to match the efficiency. So then it basically becomes a kind of economically balanced supply function.
Shop smart with your Bitcoin and get 3% back with Gift. On Gift, you can get gift cards with Bitcoin. Choose from over 200 retailers, including Target, GameStop, Gap, and more. Gift makes it easy to shop on Android or on the web. There are no additional fees, and when you shop with Bitcoin, you get 3% back. Go ahead, try Gift. That's GYFT.com.